All right, let's go. Number 10. The Dunkleosteus, the armored nightmare that may never have left the deep. In 1873, fossil hunter J. Terrell was walking the cliffs along the shore of Lake Erie in Ohio when he uncovered something that defied every assumption 19th century paleontologists held about ancient seas. Buried in black shale, 360 million years old, Terrell found the armored skull of a creature so massive and so heavily plated that it took decades for science to reconstruct what it actually was. They called it Dunkleosteus terrelli, a predator from the Devonian period that grew up to 33 feet long, weighed nearly 4 tons, and possessed a bite force estimated at 11,000 pounds per square inch. That is stronger than a modern great white shark, stronger than a saltwater crocodile, stronger than almost anything alive in the oceans today. Dunkleosteus did not have teeth in the traditional sense. Instead, its jaws were lined with 2 pairs of sharp, bony plates that sheared against each other like industrial blades, capable of slicing through shell, bone, and armored fish with mechanical efficiency. Its head and thorax were encased in thick, bony armor, giving it the appearance of a submarine wearing the skull of a monster. It ruled the Devonian oceans for millions of years before vanishing from the fossil record during one of the great mass extinctions, its reign ending in what scientists call the Hagenberg event roughly 359 million years ago. But here's where the story refuses to stay buried. Reports from deep-sea trawlers operating above abyssal trenches in the North Atlantic have described catching fragments of armored plating tangled in nets pulled from depths beyond 3,000 meters. Sonar operators on research vessels have logged biological contacts too large to be any known fish, moving slowly along canyon walls where light has never reached. Cryptozoologists who catalog these reports point to the same unsettling pattern. The sightings cluster in regions where Devonian seabeds were later buried and preserved, and where modern ocean trenches cut down into those ancient layers. What makes this particularly unsettling is the math of extinction itself. We assume that creatures disappear when their ecosystems collapse. But the deep ocean below 2,000 meters has remained chemically and thermally stable for hundreds of millions of years. It is the most unchanging environment on the planet. A predator that adapted to cold, dark, high-pressure water during the Devonian would find almost nothing different about those same waters today. The surface world died. The abyss did not. The implications extend further into territory most marine biologists refuse to discuss publicly. If a relict population of Dunkleosteus or something descended from it survived in the deep, it would have had 360 million years to adapt to the crushing pressures and eternal darkness of the abyssal plain. Its armor would be thicker. Its eyes would be larger or gone entirely. Its bite would have grown stronger. Refined by hundreds of millions of years of hunting in conditions we cannot survive for 30 seconds without a submersible. Consider the metabolic evidence. Creatures in the abyss slow down. Their life cycles stretch. Greenland sharks live for 400 years. Deep-sea tube worms live for centuries. A Dunkleosteus lineage that descended into the abyss would not have evolved to hunt faster. It would have evolved to wait longer, to ambush from the dark, to sit motionless against canyon walls for weeks at a time until something living passed within range of its armored skull. The Devonian surface predator would have become something else entirely. A patient thing, a still thing, a thing that exists in the spaces between submersible expeditions. You would never see it coming. At 3,000 meters depth, visibility is effectively zero. The only warning would be pressure, the displacement of water as something the size of a bus moved through the black toward your vessel. And then the sound of those bony shears closing on the hull. Number 9, the Helicoprion, the spiral-jawed hunter that science still cannot explain. In 1899, Russian geologist Alexander Karpinsky published a description of a fossil so bizarre that for over a century, paleontologists could not agree on what they were looking at. It was a perfect spiral of teeth, coiled like a circular saw blade, belonging to a creature that swam through the oceans 270 million years ago during the Permian period. Karpinski named it Helicoprion, the spiral saw, and for the next 114 years, every reconstruction of where that tooth whorl sat in the animal's body was wrong. It was not until 2013, when researchers at Idaho State University used CT scans on a fossil specimen, that the truth emerged. The tooth spiral was embedded in the lower jaw, a rotating buzz saw of serrated teeth that grew continuously throughout the animal's life, with new teeth pushing the older ones into the spiral at the center. Helicoprion was a shark-like predator estimated at 25 feet in length, possibly larger, with a jaw mechanism unlike anything else that has ever existed on Earth. When it bit down, the spiral rotated backward, drawing soft-bodied prey into its throat while simultaneously slicing it into pieces. Helicoprion is supposed to have gone extinct during the Permian-Triassic extinction event, the largest mass die-off in Earth's history, which eliminated 96% of marine species. But here is what the textbooks do not emphasize. Helicoprion's closest living relatives are not sharks. They are the ratfish, a group of cartilaginous deep-sea dwellers that still patrol the abyssal zones of every ocean on the planet. The family line never fully ended. It went down. Fishermen working the deep long lines off the coast of Chile have reported a recurring phenomenon that has no accepted scientific explanation. Hooks set at depths of 1,500 to 2,000 meters come back sheared cleanly in half, the steel cut as if drawn through a rotating blade. Baitfish are found not bitten, but ribboned, their flesh sliced in parallel strips consistent with a circular cutting motion. Marine biologists have proposed gigantic squid, unknown shark species, and mechanical failure. None of the explanations fit the cutting pattern. What makes this particularly disturbing is the preservation potential of Helicoprion's environment. The creature hunted in mid-depth waters during the Permian, the exact ecological zone that has changed the least in the 250 million years since. Mesopelagic and bathypelagic waters cycle their chemistry slowly. Temperature at 2,000 meters has shifted by only a few degrees across geological ages. If any Permian predator could have slipped through the extinction bottleneck by retreating deeper, Helicoprion's morphology suggests it was already specialized for exactly that retreat. The implications for deep-sea exploration are chilling. A 25-foot predator with a self-renewing spiral of serrated teeth would have no natural enemies in the modern abyss. It would hunt whatever it could draw into that rotating jaw, and there is no reason to assume it would distinguish between a giant squid and a deep submersible. The submersible Alvin has logged thousands of hours on the abyssal plain without incident. That absence of encounter tells us either the creature is extinct, or it is rare, or we have simply been lucky. The mathematics of the spiral jaw are worse than they appear. A rotating tooth whorl that grows continuously across the creature's lifespan means Helicoprion never dulled, never broke its dentition, never lost its cutting edge. Every tooth it ever grew is still mechanically available to it. A 25-foot adult could have carried hundreds of serrated teeth in its spiral, arranged in a coil that functioned as both weapon and archive. Modern sharks lose teeth constantly. They shed and regrow and compromise. Helicoprion did not compromise. It accumulated. A deep adapted descendant, slowed by abyssal cold and extended by abyssal longevity, could carry a cutting spiral refined across centuries of its own life. You do not want to be the dive that stops being lucky. Number 8. The Livyatan, the sperm whale that ate other whales. In 2008, paleontologist Klaus Post was cataloging fossils at the Museum of Natural History in Rotterdam when he pulled open a drawer and found a tooth so large he initially assumed it had been mislabeled. It was 36 centimeters long, roughly 14 inches, and it belonged to a predatory whale that had lived 9.9 million years ago in the warm oceans of the late Miocene. When the full skull was finally excavated from the Pisco Formation in Peru, the creature was given a name that reflected its impossible scale: Livyatan Melville, a reference to the biblical sea monster and to Herman Melville, the author who gave us the white whale. Livyatan was a sperm whale, but not like the sperm whales alive today. Modern sperm whales have teeth only in their lower jaw and feed primarily on squid, using echolocation to hunt in the deep. Livyatan had teeth in both jaws, each one the size of a bowling pin, and its skull anatomy indicates it fed on other whales. Fully grown, Livyatan reached lengths of 43 to 57 feet and possessed a bite force that would have allowed it to crush the skull of a baleen whale in a single strike. It was the apex predator of its ocean, a creature that hunted animals as large as itself. The official story is that Livyatan went extinct around the end of the Miocene, roughly 5 million years ago. As cooling oceans altered the distribution of its prey, and new predators, such as the ancestors of modern orcas, filled the competitive niche. But here is where the oceanographic record refuses to cooperate with the tidy extinction narrative. Whale carcasses found drifting in the southern Pacific over the past 30 years have occasionally shown bite marks that do not match any known modern predator. The spacing between tooth impressions is too wide for a great white shark and for a modern orca. The depth of penetration suggests a bite force beyond anything documented in living cetaceans. What makes this particularly compelling is the behavioral pattern of deep-diving sperm whales. Modern sperm whales descend to depths of 2,000 meters or more, spending long periods in waters where human observation is effectively impossible. They hunt giant squid in the lightless zone, returning to the surface only to breathe. If a related species of macropredatory whale had survived in smaller numbers by shifting its hunting behavior into the deep, it could exist as a rare, mostly invisible population, surfacing only briefly and in remote regions of open ocean where no human is ever present. The implications for what happens in the deep ocean shift from abstract to personal. Livyatan hunted by echolocation, meaning it located prey through sound, not sight. In the darkness of the deep, a 50-foot predatory whale would detect a submarine or a submersible from miles away. It would know the shape, the size, and the interior layout through pulses of sonar more refined than any human instrument. And unlike the Dunkleosteus or the Helicoprion, Livyatan is a mammal, an air breather, meaning it surfaces. The most terrifying aspect is not the possibility of encountering one in the deep. It is the possibility of one surfacing beside a small vessel at night, in open ocean, 1,000 miles from help, and being recognized by a creature that has learned across millions of generations to treat anything that breathes as potential prey. The echolocation capacity is what elevates Livyatan from a creature to a concept. Modern sperm whales produce the loudest biological sounds on Earth, clicks measured at 230 decibels, powerful enough to physically disorient prey and stun smaller animals at close range. Livyatan's skull was proportionally larger, and its spermaceti organ more massive. Its clicks would have been weapons. A surviving population would not simply locate vessels in the deep. It would probe them, map them, test them with pulses of sound that could induce vertigo in any human unlucky enough to be submerged nearby. The creature would know the interior of a submersible before its operators knew the creature existed. You would hear the breath before you saw the shape. Number 7. The Basilosaurus, the serpent whale that never truly left. In 1834, fossil hunters in Louisiana began unearthing enormous vertebrae from swampy ground that had once been the floor of a prehistoric sea. The bones were so long and so numerous that the creature was initially classified as a marine reptile and given the name Basilosaurus, the king lizard. It took several more decades of anatomical study before scientists realized they had misidentified it entirely. Basilosaurus was not a reptile. It was a whale, an early ancestor of all modern cetaceans that had lived 40 million years ago during the Eocene epoch, when the oceans were warm and the continents had not yet reached their current positions. What made Basilosaurus terrifying was its form. It grew to lengths of 60 to 66 feet, but unlike modern whales, its body was long and serpentine, with a relatively small head and a tail that undulated in horizontal waves. Witnesses observing a living Basilosaurus from a boat would not have seen a whale. They would have seen a sea serpent. Its jaws were lined with interlocking teeth designed for shearing flesh, and isotope analysis of its fossil teeth indicates it was a pure carnivore, hunting sharks, large fish, and smaller early whales throughout the Eocene oceans. Basilosaurus is believed to have gone extinct roughly 34 million years ago, as ocean cooling at the end of the Eocene reduced the warm water habitats it relied on. But here is where the pattern that has haunted marine folklore for 3,000 years begins to make uncomfortable sense. Sea serpent sightings, documented in logs and journals across every century of recorded maritime history, describe a remarkably consistent creature. Long, snake-like body, small head, undulating horizontal motion, length estimates typically between 50 and 80 feet. The description matches Basilosaurus with a precision that cannot be coincidence and cannot be independently invented by thousands of unconnected witnesses across multiple continents and centuries. What makes this particularly unsettling is what happened in 1848. The crew of the HMS Daedalus, a British warship crossing the South Atlantic, reported a sea creature passing within 100 yards of their vessel in broad daylight. The captain, 7 officers, and multiple crew members all observed the same animal for roughly 20 minutes. They described it identically. A serpentine body at least 60 feet long, a small head held above the water, undulating motion, and a speed that suggested a powerful tail propulsion system beneath the surface. The incident was reported to the Admiralty and published in the Times of London. No known animal, living or extinct, matches the description as closely as Basilosaurus. The implications stretch across the folklore of every seafaring culture on Earth. The Norse kraken stories, the Greek accounts of sea monsters, the Scottish Loch Ness tradition, the descriptions from Polynesian navigators. The pattern is not random. It points toward a species that survived in diminished numbers in warmer ocean regions, occasionally surfacing in warm currents and remote passages where ships were rare and witnesses were isolated. As global shipping grew denser in the 20th century, the sightings did not stop. They simply moved further from shore, into waters few vessels cross. Basilosaurus was a breathing mammal. It needed air. Any surviving population would still need to surface, which means it is still possible occasionally for a small boat in the wrong latitude at the wrong hour to witness something the crew will later doubt they ever saw. The ecological case for survival is stronger than most marine biologists acknowledge. Basilosaurus was an opportunistic carnivore with a wide thermal tolerance. Its body plan was serpentine, meaning it required less energy to move than a modern thick-bodied whale. It hunted in coastal and pelagic zones both. Of all the extinct cetaceans in the fossil record, Basilosaurus had the fewest specialized requirements for survival. It needed warm water, breathable air, and prey. All 3 of those conditions exist today in the Indian Ocean, the South Pacific, and the Coral Sea, exactly the regions where modern sea serpent sightings cluster most densely. The extinction hypothesis assumes the creature required Eocene conditions specifically. The behavioral evidence suggests it did not. You would question your eyes. The ocean would not care. Number 6. The Megalodon, the shark that refuses to stay extinct. In 1667, Danish naturalist Nicholas Steno examined a set of massive triangular teeth that had been recovered from Mediterranean coastal sediments, and he made a claim that contradicted every accepted theory of his era. The teeth were not, as most scholars believed, the petrified tongues of stone dragons. They were the teeth of an enormous shark that had once swum in ancient seas. Steno was correct. The creature he had identified would eventually be named Otodus Megalodon, a shark that ruled the world's oceans from roughly 23 million years ago until its accepted extinction around 3.6 million years ago. Megalodon grew to lengths between 50 and 65 feet, with some estimates pushing higher. Its teeth measured up to 18 centimeters along the diagonal, nearly 3 times the size of a great white shark's largest teeth. Its bite force has been estimated at up to 40,000 pounds per square inch, the most powerful bite ever evolved in the history of life on Earth. It hunted whales by biting off their fins and tails to immobilize them, then returning to consume the rest. It was not merely the largest shark that ever lived, it was the largest active predator the oceans have ever produced. The official extinction date places Megalodon's disappearance at the end of the Pliocene, attributed to cooling oceans, shifting prey distributions, and competition from newly evolved predators. But here is where the scientific consensus begins to strain against its own evidence. In 1918, Australian naturalist David Stead recorded the testimony of an entire fleet of experienced fishermen from Port Stephens who refused to put out to sea for days after an encounter with what they described as a ghostly white shark, at least 115 feet long, that had taken their lobster pots in a single pass. These were men who had spent decades on the water. They knew every species in their waters. They saw something they could not name. What makes this particularly disturbing is the deep sea evidence. In 1875, the research vessel HMS Challenger dredged megalodon teeth from the Pacific seafloor that were later radiometrically dated to be only 10,000 to 15,000 years old. The dating was disputed. It has been explained and re-explained, but the teeth exist, and the argument that they could be that recent has never been definitively closed. If accurate, the dating would mean Megalodon survived into the period after the last ice age, into the window of early human civilization. The implications have pushed a portion of the marine biology community into a position they will not defend publicly, but will acknowledge privately. The deep ocean is almost entirely unexplored. The abyssal zones between 3,000 and 6,000 meters remain less mapped than the surface of Mars. A reduced population of deep adapted megalodon, shifting its hunting behavior to ambush whales during their deep dives, could exist in numbers too small to appear in standard surveys and in regions too remote to be observed. The oceans contain more than 360 million cubic kilometers of water. We have directly observed a fraction of 1% of that volume. The mathematics of observation work against us. A creature does not need to be abundant to exist. It needs only to be present in numbers large enough to reproduce and small enough to remain invisible. Megalodon survived in warm pelagic waters for 20 million years. Its potential descendants would have had 3.6 million years to refine themselves for the deep. Consider what deep adaptation would require and what it would produce. A megalodon lineage pushed into the abyss would lose its pigmentation first. The ghostly white coloration described by the Port Stephens fishermen in 1918 matches exactly the depigmentation pattern seen in every deep sea shark species known to science. Its eyes would enlarge to capture bioluminescent signals. Its metabolism would slow, extending its lifespan from decades to potentially centuries. Its hunting pattern would shift from pursuit to ambush, striking at whales during their deepest dives when the animals are already exhausted and oxygen depleted. Every pressure that killed the surface population would refine the survivors into something more efficient, more patient, and more invisible than the original species ever was. The Megalodon of the Miocene is extinct. Whatever may have taken its place in the deep would not be the same animal. It would be colder, slower, larger across the length of its own lifespan. A predator that learned patience from an environment that rewards nothing else. It would not chase, it would wait, and the ocean would bring prey to it the way the ocean has always brought prey to the things that learned to stop moving. You do not need to see it to be hunted by it. You only need to be in the water it has chosen. Number 5, the Mosasaurus, the marine reptile that ruled the Cretaceous seas. In 1764, quarry workers cutting limestone in a mine beneath St. Petersburg, near the Dutch city of Maastricht, uncovered a skull so massive and so clearly predatory that it triggered a legal battle between nations. French forces eventually seized the fossil during the Napoleonic Wars, and in 1822, the creature was formally named Mosasaurus hoffmanni. It was not a dinosaur. It was a marine reptile, a distant relative of modern monitor lizards and snakes that had evolved to dominate the oceans during the final 20 million years of the Cretaceous period, ruling the seas from roughly 82 million years ago until the extinction event that ended the age of dinosaurs 66 million years ago. Mosasaurus grew to lengths of 56 feet, possibly longer. Its jaws were lined with conical piercing teeth, and a second set of pterygoid teeth set in the roof of its mouth, an anatomical feature shared with modern snakes, allowing it to drag prey inward and swallow items larger than its own head. Its body was streamlined and propelled by a powerful tail fluke that had evolved convergently with the tail shapes of sharks and cetaceans. It ate everything: fish, sharks, other marine reptiles, even smaller members of its own species. Isotope analysis of Mosasaurus teeth indicates it was warm-blooded, an active high-metabolism predator that could pursue prey at sustained speeds. The Cretaceous-Paleogene extinction event supposedly ended the lineage along with the non-avian dinosaurs. But here is where the extinction narrative cracks against its own evidence. The asteroid impact that killed the surface ecosystems produced its most severe effects in shallow waters and photic zones. Deep marine environments below 1,000 meters experienced dramatically reduced impact. Recent studies of Cretaceous-Paleogene boundary sediments show that many deep-sea lineages passed through the extinction event with their populations largely intact. Mosasaurus was a breath-holding reptile capable of deep dives, exactly the morphology that would have given at least some individuals the physiological range to exploit refugee depths during the collapse. What makes this particularly unsettling is the persistent pattern of sightings from remote Pacific atolls, where local fishing cultures have for centuries described a creature they call by various names across unconnected island groups, but always with the same description: a massive reptilian predator with a long tail, conical teeth, and a habit of taking fishermen from the side of small boats in shallow reef channels. The accounts were dismissed by Western researchers for 2 centuries as folklore. Then, in 2019, a research team publishing on deep reef biodiversity noted that the descriptions consistent across Polynesian, Melanesian, and Micronesian sources matched the anatomy of Mosasaurus with a precision that no surviving modern species could explain. The implications reach into the behavior of coastal predation itself. If a relict population of smaller Mosasaurus adapted to deep reef environments, it would be a coastal ambush predator that surfaces in shallow water only at night, following prey into reef channels under cover of darkness. Every culture in its range would eventually develop stories about it. Every culture would eventually stop believing those stories once outside anthropologists arrived to reclassify them as myth. The creature would continue. The silence around it would grow. The most disturbing aspect is the reproductive biology. Mosasaurus is believed to have been viviparous, giving birth to live young in open water. A relict population would not need nesting sites, would not leave eggs or egg fragments for discovery, would not depend on any terrestrial habitat at any point in its life cycle. It could exist entirely in the ocean, generation after generation, leaving no evidence except the occasional disappearance of a fisherman whose small boat was found empty at dawn. You would not see the attack. You would only see the water closing over the space where someone had been. Number 4. The Kronosaurus, the short-necked pliosaur that hunted like a battering ram. In 1899, Australian cattleman Andrew Crombie stumbled across a set of fossilized teeth in the arid soil of northern Queensland, each one nearly a foot long and shaped like blunt conical spikes. Paleontologists who examined the specimen and the subsequent skeletal finds named the creature Kronosaurus queenslandicus, after the Greek titan Kronos, who devoured his own children. The name was chosen deliberately. Kronosaurus was a pliosaur, a short-necked plesiosaur that had lived 125 million years ago during the early Cretaceous, and it was built for one purpose: killing things larger than itself. Kronosaurus grew to lengths of 33 feet. Its skull alone measured 9 feet long, by nearly a third of its total body length. It did not have a long neck. It had a massive head mounted on a powerful torso, propelled by 4 paddle-shaped flippers that moved in coordinated underwater flight. Its teeth were blunt, designed not for slicing, but for crushing. It hunted by ramming its prey at high speed, driving its reinforced skull into the bodies of other marine reptiles, large fish, and ammonites, disabling them through sheer impact before biting down with jaws capable of generating crushing force comparable to the largest marine predators that have ever existed. The official record places Kronosaurus extinction during the mid-Cretaceous, roughly 100 million years ago, as shifting ocean chemistry and competition from emerging marine predators reduced its habitat. But here is where the oceanographic data refuses to cooperate. Deep ocean trenches have been stable environments since before the Cretaceous began. The Mariana Trench is 180 million years old. The Tonga Trench is older still. A deep adapted pliosaur would have had refuge environments available to it throughout every extinction event that has occurred since its supposed disappearance. Nothing about the deep ocean requires an ambush predator of this body plan to have died out. What makes this particularly terrifying is the hunting mechanic itself. Kronosaurus did not pursue prey. It intercepted prey. Its 4-flippered propulsion system allowed it to accelerate from a standstill with extraordinary speed, striking from below with the full mass of its body behind a reinforced skull. In the lightless depths of the modern abyss, a predator using this hunting pattern would be effectively undetectable until the moment of impact. Submersibles record nothing unusual on sonar. The water around them appears empty. And then a 33-foot ramming predator arrives from directly beneath at a closing speed that would destroy any small research vessel in a single collision. The implications become more uncomfortable when you examine the loss records of deep-sea research vehicles. Unmanned submersibles have been lost in abyssal trenches for decades without explanation. Cables have sheared. Hulls have failed. The incidents are attributed to pressure failure, implosion, equipment malfunction. Every case is investigated individually. No one compiles the pattern. No one maps the locations of the losses against the theoretical range of a surviving ambush predator from the Cretaceous. The data exists. It has simply never been assembled. Kronosaurus was an air breather. Any surviving lineage would have had to either evolve extended breath-holding capabilities far beyond anything in the modern animal kingdom, or surface occasionally in regions where no human ever witnesses the event. Sperm whales dive for 90 minutes. A specialized descendant of Kronosaurus could potentially exceed that. Its surfacing behavior would occur in remote equatorial ocean at night, in weather conditions that keep vessels away, in the tiny statistical windows where the ocean is genuinely unwatched. You would feel the strike before you heard the impact. The submersible would be silent. And then it would not be. Number 3. The Tylosaurus, the hypercarnivore, that left evidence of its own cannibalism. In 1918, paleontologist Charles Sternberg unearthed a Tylosaurus specimen in western Kansas that contained, preserved within its ribcage, the partially digested remains of another smaller Tylosaurus. The fossil was not unique. Multiple Tylosaurus specimens have been found with the bones of their own species in their stomachs. The creature was a mosasaur, closely related to the Mosasaurus of Entry 5, but faster, more streamlined, and considerably more aggressive. It grew to lengths of 46 feet during the late Cretaceous, 85 to 80 million years ago, and it fed on anything that moved in the western interior seaway that once covered central North America, including its own kind. Tylosaurus had an elongated bony snout that it used as a ramming weapon before the bite, stunning large prey before its jaws closed. Fossil skulls recovered from Kansas and South Dakota show healed fractures consistent with the creature surviving head-on collisions with prey animals that would have killed any modern predator outright. Its bones were built for violence. Its teeth were recurved and interlocking, designed to prevent prey from escaping once caught. It hunted sharks, plesiosaurs, large fish, diving birds, and juvenile mosasaurs from other species. And it hunted juveniles of its own species when the opportunity presented itself. The extinction story is the same as Mosasaurus, the asteroid at the end of the Cretaceous, the global collapse, the accepted end of the mosasaur lineage 66 million years ago. But here is the detail that should complicate the story, and rarely does. Tylosaurus fossils show evidence of deep-diving anatomy, its bone density patterns, its sclerotic ring dimensions, its nostril placement all indicate it spent significant portions of its life in deep water, potentially exceeding the dive depths of modern sperm whales. It was not a surface predator that occasionally went deep. It was a pelagic hunter capable of exploiting water columns from the surface down to depths where Cretaceous shallow water ecosystems simply ended. What makes this particularly compelling is the recurring pattern in 20th century whaling logs. Crews operating in the North Pacific during the early decades of industrial whaling reported a phenomenon they called gray attackers. Unidentified large marine predators that would appear near harpooned whales, tearing pieces from the carcasses before the whaling vessels could complete recovery. The crews described long, streamlined bodies, bar ramming attacks, and a hunting style fundamentally different from any shark or orca they had encountered. The reports were logged, filed, and never investigated. The whaling industry collapsed before anyone compiled the records. The implications of a surviving Tylosaurus population are unique among deep-sea predator theories. Because the creature was a confirmed cannibal, a relict population could sustain itself through internal predation when other prey was scarce. Modern predator populations crash when their food sources decline. Tylosaurus would eat its own juveniles, its own wounded, its own old. The population would shrink during hard times and expand when conditions improved, but it would never fully collapse. The cannibalistic behavior documented in the fossil record is not a curiosity. It is a survival mechanism that would allow the lineage to persist through environmental changes that wiped out every other large marine predator. The deep ocean would suit this behavior perfectly. Populations would remain small and spread across enormous ranges. Encounters between individuals would be rare enough to reduce social disease transmission. Reproduction would occur at specific temperature thresholds, and the cannibalism would handle population regulation without requiring any external predator to intervene. The species would become invisible through dispersion and self-regulation. You would never find a body. The Tylosaurus that survived would ensure there was never a body to find. Number 2. The Shastasaurus, the colossal ichthyosaur that reached whale dimensions. In 1895, a partial skeleton recovered from Triassic strata in California was described by paleontologist John Campbell Merriam, who gave it the name Shastasaurus after the Shasta region where the fossil was found. For decades, the creature was reconstructed as a relatively ordinary ichthyosaur, a dolphin-shaped marine reptile from the late Triassic, roughly 210 million years ago. Then, in 2004, paleontologists examining a massive incomplete skeleton from British Columbia announced a revised size estimate that shocked the field. Shastasaurus sicaniensis had reached lengths of 69 feet. It was one of the largest marine predators in the history of Earth, rivaling modern sperm whales in body mass. Shastasaurus was a suction feeder. Its jaws were relatively narrow and toothless, or near toothless in adults, and its feeding mechanism involved rapid expansion of its throat cavity to inhale soft-bodied prey at close range. It hunted squid and squid relatives in the deep waters of Triassic oceans, diving to depths estimated at over 1,000 meters to exploit the same ecological niche that modern sperm whales occupy today. It was not a shallow water predator. It was built for the deep, and everything about its anatomy confirms that deep water was its primary habitat. The accepted extinction date places Shastasaurus and its closest relatives at the end of the Triassic, roughly 201 million years ago, killed by the Triassic-Jurassic extinction event. But here is the evidence that complicates the narrative. The extinction event had its greatest impact on shallow water and terrestrial ecosystems. Deep pelagic zones experienced substantially lower mortality, and Shastasaurus was not a shallow water species. Its hunting behavior, its body plan, its feeding mechanism, every anatomical and behavioral marker indicates it lived most of its life in the same deep environments that passed through the Triassic-Jurassic boundary with minimal disruption. What makes this particularly disturbing is the prey overlap. Shastasaurus hunted cephalopods. The modern deep ocean is dominated by cephalopod populations that exceed the combined biomass of every vertebrate species in the ocean. Giant squid, colossal squid, and hundreds of lesser-known deep-dwelling cephalopod species occupy the same ecological niche that Shastasaurus evolved to exploit. The food source has not only persisted, it has flourished. A surviving Shastasaurus lineage would have had uninterrupted access to its primary prey for 200 million years across every climate shift, every extinction event, every chemical change in the oceans since the Triassic began. The implications for what exists in the deep shift from speculation toward probability. An air-breathing 69-foot suction feeder with the endurance to dive past 1,000 meters and the patience to hunt giant squid in perpetual darkness would be nearly impossible to detect using modern survey methods. Sperm whales are difficult to study because they spend most of their lives below observable depths. A species with even greater dive capacity and a smaller population would be effectively invisible. Sonar contacts would be dismissed as whales. Visual sightings from surface vessels would be dismissed as whales. The species could exist in reduced numbers across every ocean on the planet, and human observation would consistently misclassify it as something else. The behavioral difference is what should concern anyone who dives near deep water at night. Sperm whales are generally indifferent to human vessels. They hunt squid and ignore ships. A Triassic suction feeder that predates the evolution of cetaceans by 150 million years would have no inherited recognition of vessels as dangerous, no learned avoidance of boat traffic, no ecological reason to distinguish between a diver and a large soft-bodied prey item drifting in the water column at night. The mistake would occur in silence. The suction would be sudden. You would not drown. You would be swallowed before drowning became relevant. The stomach acids of modern ichthyosaur analogs, reconstructed from fossilized gut contents, are aggressive enough to dissolve bone within days. Consciousness, if preserved through the initial suction, would end long before digestion completed. Number 1. The Liopleurodon, the ocean apex that the fossil record cannot fully size. In 1873, French paleontologist Henri-Émile Sauvage described a set of teeth from late Jurassic strata in France, teeth so large that he was forced to assume they belonged to an undescribed giant pliosaur. He named the creature Liopleurodon ferox. In the 150 years since, the size of Liopleurodon has been continuously revised upward as new fragments have emerged. The accepted length today ranges from 20 to 33 feet. But isolated fragments of larger individuals keep surfacing from Jurassic deposits across Europe, each one suggesting that the creature reached sizes the textbooks are reluctant to commit to. Some estimates based on jaw fragments push toward 50 feet. The official record refuses to confirm it. The fragments keep being found. Liopleurodon was a pliosaur, the same lineage as Kronosaurus, but from roughly 160 million years ago, during the late Jurassic. It had the same body plan: short neck, massive skull, 4 powerful flippers for underwater flight, conical piercing teeth. It was an ambush predator at the top of its food chain, and its sense of smell, reconstructed through analysis of its nasal anatomy, appears to have been extraordinarily developed. Liopleurodon hunted by scent in the water column, detecting prey from kilometers away through directional olfaction, a capability that allowed it to locate individual animals across vast dark ocean ranges. The extinction record places Liopleurodon at the end of the Jurassic, 145 million years ago. But here's the detail that has haunted cryptozoology since the discipline was first assembled. Jurassic deepwater deposits are rare because Jurassic deepwater environments have mostly been subducted or uplifted since the period ended. The fossil record of Jurassic deep ocean predators is not a record of what lived there. It is a record of what we have been able to recover. The absence of post-Jurassic Liopleurodon fossils does not prove the creature went extinct. It proves only that we have not found its fossils, and the places where its fossils would be preserved if it survived are exactly the places we cannot reach. What makes this the most disturbing entry on the list is the olfactory hunting capability. A predator that locates prey through scent trails in water does not need visual contact with its target. It does not need sonar signatures. It does not need to pursue. It follows chemical gradients across kilometers until it arrives at the source. Divers bleed. Submersibles leak. Research vessels discharge. Every human activity in deep ocean environments produces chemical signatures that propagate through the water column. A Liopleurodon lineage adapted to the deep would detect those signatures at ranges that no modern marine predator can match. The implications extend into the statistical structure of deep ocean losses. Across the history of deep submersible operations, a small but persistent number of vehicles have been lost or damaged under circumstances that remain formally unexplained. The official explanations cite equipment failure, pressure miscalculation, operator error. The pattern is never compiled across operators or across decades because no single organization has a reason to compile it. If a relict Liopleurodon population used olfactory hunting to locate chemical anomalies in deep water, the creature would investigate exactly the kinds of vehicles that humans send into the abyss. It would not hunt them intentionally. It would simply arrive at their locations, and arrival alone for a predator of that mass would be sufficient to end the encounter. The most terrifying aspect is the logic of probability across 145 million years. Evolution does not require success. It requires survival. A single Jurassic pliosaur lineage that found its way into a deep refuge habitat, reproduced successfully, and maintained a viable population across the Cretaceous-Paleogene extinction, the Eocene cooling, the Ice Ages, and every oceanographic upheaval since would not need to be abundant today. It would need only to exist. The mathematics of deep ocean concealment are forgiving enough that a population of a few hundred individuals could persist across every ocean basin on Earth without producing a single confirmed sighting. The ocean covers 361 million square kilometers. Its average depth exceeds 3,600 meters. Its total volume is nearly 1.3 billion cubic kilometers of water. we have visually surveyed less than 5% of it. Every creature that has ever been believed extinct based on the absence of fossils has been believed extinct based on the absence of evidence in a tiny sampled fraction of the habitat where that creature would actually live. Consider the sensory asymmetry. Human submersibles detect their environment through sonar, cameras, and pressure sensors, all of which operate within narrow physical ranges, and all of which announce their own presence through the energy they emit. Sonar pings. Lights illuminate. Propellers vibrate. Every instrument humans use to see the deep also broadcasts the vessel's position across hundreds of meters of water. A Liopleurodon descendant hunting by scent would detect those broadcasts through chemical diffusion patterns disturbed by motion and heat. The vessel would announce itself long before the vessel itself could see anything. The predator would arrive unseen, scent locked on a target that had been calling out in every direction for hours before the operators realized they were being approached. By the time a visual contact occurred, the encounter would already be concluding. You assume the ocean is mapped. It is not. You assume these creatures are gone. You have no way of confirming it. You assume the deep is empty. The deep has never been empty. And everything that ever lived there and adapted to stay there is almost certainly still there, waiting in the dark water that has not changed for 200 million years, while human civilization scratches at the surface of a world it has only ever seen the top layer of. If you want to see more videos like this, click the video on screen now and make sure to subscribe.